Hi, I'm Tim. Join me in this video as I go over center of gravity considerations for RC model airplanes, what the CG is, how you determine it, how you find it on the plans, and why it's absolutely crucial for the safe flying of your RC model airplane. Let's get to it. The center of gravity is a critical computation for any aircraft from a Boeing 747 to your RC model airplanes. If an aircraft doesn't have the proper center of gravity, it's probably going to crash. And we will discuss the importance of that throughout this video. I'll show you how to find the location of the center of gravity and the symbology on plans, discuss a range of CGs, discuss the importance of center of gravity for full-scale aircraft to include aircraft on the ground that they don't follow the center of gravity considerations will literally fall back on their tails. And this will be at the end of the video. There's a number of airliners that have literally fell over on their tails, not being aware of center of gravity considerations. And we'll also discuss the consequences of having the wrong center of gravity either too far forward or too far aft for your RC model airplane. So what is the center of gravity? The center of gravity is a point where the average weight of the aircraft meets. What that means in more plain language, it's literally a balance point of an airplane for a center of gravity. A good demonstration of the center of gravity is with my foam board model, the F-22. By the way, I'll be showing several of my models throughout this video. If you'd like more information on those models, there'll be a link in the description to the video on this model. But at any rate, you can see the F-22. It's really a pretty good design. There's very little weight up front. The motor's back here, the control surfaces. And what I did is I was constructing it. This joining line between two foam panels to complete the wing is the location of the center of gravity from the plans. And so when I say suspended, if I pretend that there's a line or a rope holding this, in this case my fingers, you can see the plane is incredibly tail heavy. That is to be expected with a motor. But what happens on this design is there's a 3-cell LiPo. The LiPo is in the battery compartment down below. And when I hold it at that point, you can see the battery adjust the weight so the center of gravity, the plane is level when held at the center of gravity. This concept of a balance point for center of gravity applies for any airplane. If you could find some magic huge crane to balance the 747 at the center of gravity, it should balance level when it's loaded for the proper center of gravity location. Another thing about center of gravity is it has a range. It's not just necessarily one point on the airplane. It can typically be a range from a forward CG to an aft CG. The amount of the range of the CG depends on the design of the aircraft. This is all part of the design process. And we'll go into more detail after this chapter on the effects of a forward or aft CG on how that airplane will handle. But the CG does have a range. For the majority of our models, it's just a single point for the center of gravity. For RC models, it's very easy just to use our fingers to balance the airplane. So this is a Guilo's Maranca. If I put my fingers about at the CG point, which is about here on the model, you can see the model balances out. If it was nose heavy, it'd be nose down. If it was tail heavy, it'd be tail down when balanced at the center of gravity. And again, the fingers are enough. These are some good illustrations on the center of gravity. Your fingers are in the CG range. Good CG, a little bit nose heavy. You're going to have to add some weight to the tail or reduce the nose weight. And here we are tail heavy. You have to add weight to the nose or reduce weight in the tail. If you want a little bit more precision, you've got a larger scale model, an acrobatic model. There are any number of CG balancers out there. I'll show a picture of one of those, and those are pretty easy to find with a Google search. And of course, the plane balances right side up or upside down. It's just a balance point for the center of gravity. One quick item on the center of gravity for full-scale airplanes. Obviously, we're not going to be hanging any airplane from the ceiling to determine the center of gravity. What happens is the aircraft technicians will put scales under the landing gear. The scales will measure the weight of the wheel, the aircraft at each point. There's data lines, various computations that can be done to pretty quickly determine the center of gravity location for that full-scale airplane. That is important to make sure the plane is built to achieve that center of gravity And also if there's any modification or changes to the aircraft, perhaps you put on a new engine, a couple new engines for multi-engine aircraft, extensive structural modifications. You've got to ensure that the plane balances out, and you do that very easily with scales. And the FAA has all their own rules for when you have to check or update the center of gravity for that particular airframe. The bottom line, though, is the plane has to balance at the center of gravity. You have to do whatever is necessary to balance that airplane on the ground before you fly. It could be adding weight to the nose, adding weight to the tail, but you have to balance out the aircraft. A good example of this is the Aeronca. It's a little bit short nose moment. These planes always tend to come on a little bit tail heavy with the structure in the tail. Weight is super important on these Guilos models, but I'll show you that I had to install some weight. A couple iron bolts had to be glued into the nose to allow this airplane to properly balance. As I mentioned briefly before, the center of gravity is typically a range for most aircraft. For models, it's usually a point. For full-scale aircraft, there is a range of center of gravity. The reason for this is the center of gravity will change throughout the flight. You could have a large airliner burning fuel. You could have passengers walking around. You could have cargo that has to be placed at a certain location. So there is a range that is allowed depending on what the aircraft designer has come up with their computations. If the center of gravity is the forward edge of the range, that's probably a little bit safer compared to aft. If the CG is a little bit further forward, you'll be a more stable aircraft. But if you're flying that airplane, you're going to have a little bit more back pressure because the elevator, the nose is going to want to tend to go down. The elevator is going to have to lift the nose up. By lifting the nose a little bit higher due to the forward CG, what you're doing is increasing the angle of attack on the wing. The angle of attack of a wing, in very simple language, is just how hard the wing is working to produce lift. So by having a forward CG, making the wing work a little bit harder, you're increasing the drag, the induced drag due to lift with that forward CG. Also with a forward CG in a full-scale aircraft, as you have to apply back elevator to keep that nose up, as you're slowing down, let's say in the flare of a landing, you could be coming back in the elevator and go to the full stop of the elevator and not have enough elevator authority to keep the nose from hitting fairly hard. You just run out of pitch control in that case. So that's just something to keep in mind with a forward CG. An aft center of gravity, on the other hand, is a more concerning one for modelers, full-scale aircraft. As the center of gravity moves further aft, there's less elevator control needed to control the pitch, so the elevator becomes a lot more sensitive. And also because the elevator is doing less work to keep the nose up, there's a little bit lower angle of attack for the wing, which means a little bit less lift. This is important for many full-scale aircraft airliners because with an aft CG, assuming you have proper control with the elevators, the reduction in the angle of attack, the decrease in drag, allows for a longer range of that aircraft. It can just fly further. I know when I was flying the CRJ-700, it was a 70-seat regional jet. We had to do a weight and balance computation for every takeoff, as every aircraft has to do. But we would have, because it just had 70 seats, would have two zones that the engineers told us to consider, Zone 1 and Zone 2. There had to be certain minimum weights in each zone. It was not unusual that we'd have to move passengers from an aft zone to a forward zone to make sure we're at the proper center of gravity, depending on the fuel load for that flight. By the same token, with the CRJ-700, when we would fly occasionally with no passengers on a repositioning flight, the designers assumed there'd be some number of passengers in the back. We would actually have to add several 50-pound sandbags to the cargo compartment to make sure that the plane properly balanced out with no passengers on board. And there are some very advanced aircraft that actually will move will move fuel between tanks during flight to achieve the proper center of gravity. A very good case of this is the Concorde, the supersonic transport. Because of the unique aerodynamic features of supersonic flight and trim associated with those extremes of flight, and the Concorde went twice the speed of sound, which is very fast. There's not too many airplanes that can go twice the speed of sound. They would actually, during the supersonic portions, transfer fuel from very aft tanks to forward tanks, back and forth, whatever was required to keep the airplane in trim. And then, of course, having to put the fuel back in the original state for landing during subsonic flight during the recovery. So again, just another emphasis on the importance of CG, center of gravity, understanding it, and following the rules for your particular aircraft. So the main thing to consider for our radio control model airplanes is when a center of gravity is shown on the plans, or sometimes it's called a balance point on some of the older plans, make sure your model balances at that balance point when it's complete. Batteries in place, plane covered, everything in place, and you're going to have to glue in to add weight to make sure that model balances at the balance point or within the range of the CG. That is a simple must-do before you can safely go out and fly the model. So what does a center of gravity symbol look like? Well, it's a circle with 4 quadrants, 2 of them blacked in. I'll put some pictures up of that. This is just a universal symbol on radio control or free flight, any model airplane plan for the location of the center of gravity. So let's talk a little bit about how you compute the center of gravity location for a plane. Maybe you're designing your own airplane, you lost the plans, you got the plane at a swap meet. So there's really 2 types of wings we have to talk about. Either a straight wing, and I'll use the Aeronca as an example. A straight wing is very simple. The leading edge and the trailing edge are parallel. After this, I'll show you how to determine the center of gravity for a swept wing. It's a pretty easy computation. I'll walk you through that. One thing to touch upon before I go into the computation of the center of gravity will depend completely on the wing. It doesn't depend on how long the nose is, how long the tail is. It just depends on the wing. It doesn't even depend on the width of the wing, the wingspan. It's just the wing chord or the distance from the leading to the trailing edge. That's all that matters. At the end of this video, I'll show you how if a model does come out, for example, a little bit tail heavy, and you can make the nose longer so you don't have to add weight, just take advantage of the longer nose moment. That is a design consideration. So to find the center of gravity for a straight wing airplane, just measure the distance from the leading edge to the trailing edge. Let's call this 4 inches for the purposes of discussion. And what will happen is the center of gravity is between 20% back to 25% back, the distance from the leading edge, 25% of 4 inches being 1 inch. So you literally measure 1 inch back, a little bit forward. That would be your center of gravity range. I would just split the difference, about 22% of the distance back from the leading edge to the trailing edge. That is your center of gravity location. Now it's a little bit different with a swept wing. Again, these are all aeronautical design considerations. They're just common knowledge. These are done before the airplane flies. There's no wind tunnel testing. These are just calculations on the ground. So let's take a look at how to do a swept wing center of gravity calculation. So what I'd like to do now is discuss how to find the center of gravity for a swept wing airplane. So this is full size, not a full size, but this is a scaled drawing of the wing of an F4 that I'm in the process of designing. If it does fly successfully, I'll put the links in the description. But what happens is, again, for the center of gravity, you don't care about the wingspan, the sweep. It's all dependent on the chord of the wing. So in this case, the chord is going to start off with 2 inches on the tip, and the chord at the fuselage joining section is 8.5 inches. So what we do is we simply take 8.5 inches, which is a chord by the fuselage, add in 2 inches, the chord at the wing, add it together, we get 10.5 inches. We take that, we divide it by 2, and we get a figure of 5.25 inches. This 5.25 inches is the mean aerodynamic chord, the average aerodynamic chord. And here it is right here, 5.25 inches. The mean aerodynamic chord really doesn't mean anything. It's just an engineering term of description. What that means is the point somewhere along this wing where the distance from the leading edge to the trailing edge is 5.25 inches, okay? So what I do literally, what you can do is you have a ruler here, and this is 5.25 inches. I'll just put my thumb there roughly, and you just move it along here until you get a point located here, which is 5.25 inches from the trailing edge to the leading edge. This is the mean aerodynamic chord. So from this mean aerodynamic chord, this is the datum line that we use to determine the center of gravity. Again, either 20% back or 25% back along the mean aerodynamic chord. When you have a constant chord wing, the mean aerodynamic chord is the same the entire wing. That's why it's just from the leading edge. You don't have to worry about the sweep. So the mean aerodynamic chord is a datum that we use to measure for the CG location. We just extend this 90-degree angle to the fuselage, and the CG location is between here for a forward CG, here for an aft CG, here's a CG symbol, and that's where your balance point will be on the completed model with this calculation. Again, really quite easy for swept wings. I'd like to point out also that every aircraft has a center of gravity location to include almost ready-to-fly models. Now, back in the days when we were building our own models from kits, from plans, and so forth, the center of gravity was just something you had to do. Very often these kits, well, just about all the time, come out of the box with everything designed for the proper center of gravity, again, with the battery installed. But notice also in this pitch, there's a very slight sweep to the leading edge of the top wing. This would be a little bit complicated, and then there's a stagger between the leading edge of the front and back. So it's going to be a little bit complicated on the center of gravity, but that's what the instruction book is for. So let's take a quick look at the E-Flight Pitts instruction manual, and it very clearly has a page on the center of gravity and where that location is back from the wing leading edge. I really like the E-Flight kits. The AS3X stabilization makes all the difference in the world. Here's the instruction manual for the pits. Notice the center of gravity is right on the title. It's a highlighted page. It describes the center of gravity. To measure it in Google search, 3.5 millimeters is 1.3 inches. As I mentioned earlier with the F-22, again, it's with the engine here. It's completely tail heavy. Completely tail heavy without the battery, but the battery is located well forward. Once we hold it at that point, the plane balances out. So the important point is, as you're building from plans or designing an airplane, you may have to think early on in the design stage where you're going to locate something heavy like the battery, the motor, etc., to ensure that the airplane balances out. A good example of this is my design of the square flyer. So this is foam board. It's 20 inches square with elevons. Again, a description in the link, a link in the description. So on this plane, I did locate the center of gravity. It's just 25% of the way back, 1/4 or 5 inches back from the leading edge, and I marked at the center of gravity. That's where the plane has to balance. The problem is there was enough structure in the back of the airplane that when I reached this balance point, it was a little bit tail heavy. So what I had to do was to add some weight into the nose bolts to keep it balanced out with the battery in place. To save the weight of the bolts, what I could have done on this is extended the nose out another inch or two, because remember, the length of the nose has nothing to do with the center of gravity location. It's just the shape of the wing. By having the motor a couple inches further forward, the weight of the motor, I might have not had the need to include the bolts to achieve the center of gravity, just having a little bit lighter aircraft. Remember, whenever we fly our model airplanes, we build them, we want to do anything possible to reduce the weight. So by extending the length of the tail, the nose, to try to achieve the center of gravity without adding extra weight, that's to your advantage, just to have a lighter flying model. Here's some real-world examples of planes that didn't follow CG rules, mostly cargo airplanes, an Atlas Air 747. With a cargo aircraft, there's obviously no passengers. Depending how that cargo is loaded at the right time, you could easily make it tail heavy like here. Classic case of the Korean Air cargo. Hopefully not too much damage as they kind of settle down. Good example of a BE-146. Notice the engines are removed from the nacelles. That weight of the engines caused it to tip back. To prevent these accidents, it's very easy for aircraft to have a post that's in the back. The post will just keep the aircraft from tipping back on its tail. And finally, one more look at an MD-11 sitting on its tail. So again, I'd like to thank you very much for watching, for joining me in this video discussing the center of gravity. Center of gravity is an absolute requirement for any RC model airplane. Know where the CG is based on the plans. The quick discussion, I've showed you how to compute where the center of gravity is. Make sure that's with everything installed for flight. To include, if you have a larger model with a gas motor and a fuel tank, you should have fuel in the tank for the CG purposes. And that's another little bit of a range discussion, because as the fuel burns out, the model will become a little bit more tail heavy. Hopefully it falls within the center of gravity range for that model. So CG is important. Check it before every flight, check it as you build, and good luck with your RC flying.